Okay, so in this practical question, we have a sphere released from rest at A. Okay, so in this practical question, we have a small sphere rolling down the track at a constant length. The sphere is released from rest, and the time t is measured. If we have a look at the graph, we can see that the time t is plotted against 1 over h. Okay, so that gives us an idea of the practical setup. But again, remember, you don't need to understand exactly what's going on because that's not what's being asked. Right, so now we have a look at our graph. A student suggests that t is proportional to 1 over h. And to test the hypothesis, a graph is drawn accordingly. We've got t on the y-axis and 1 over h on the x-axis. First question asks you, sorry, it's very noisy. First question asks you to draw a straight line that best fits the data. So we have a look here. How do we know it's not a curve? Well, if you can squeeze a straight line through the points without missing a single one and going through the error bars, then it's a straight line. So let's have a go. Okay, you can see I've just about done it here. This program won't let me draw straight lines easily. So you make sure, though, that you use a ruler to do this. And as you can see, you can quite easily draw a nice straight line. Okay, now the next question, same as usual, state why the data does not support the hypothesis. What was the hypothesis? That t is proportional to 1 over h. So once again, is it a straight line? Does it go through the origin? Well, it is a straight line, but it does not go through the origin. So once again, our answer is does not go through the origin. Blink. Origin. So you can see this question comes up all the time. So now we're going to look at another relationship. Okay, so this time on the axis we have t squared. So if we have a look at the original formula, in order to make it linear, you've just squared both sides. So you have t squared equals k 1 over h. Okay, so we've gotten rid of that power, that half to the power of a half. It's true that another way that we could have done this is by using logs, but this is another just as valid way of plotting a linear relationship. So here we go. This time we have a nice proportional line because it's straight and it goes through the origin. But they're not going to ask about that again. This time we're going to be asked about uncertainties. And the uncertainty that we need to figure out is at 1 over h equals 10, which is the only error bar we have. So we're asked to work out the uncertainty. So the first thing to do is to see the value of the squares. And what we can see is that 2 squares is equal to 0.1. And if we count the amount, we've got 1, 2, 3, 4, 5, 6, 7. Okay, so 7 squares from there to there. So 7 over 2 equals 3.5, because 2 squares is equal to 0.1. 3.5 times 0.1 gives us plus or minus 0.35. Okay, and that's our uncertainty. So for question number 1, state the value of the uncertainty when 1 over h equals 10. The answer is 0.35 plus or minus. And lastly, super important, don't forget the units. Seconds squared. Depending on the mark scheme, you might lose all the marks just because you forgot the units. And you don't want that to happen. Next question. Calculate the uncertainty in t squared if t equals 0.8 plus or minus 0.1. So there are lots of steps here. We have t first. You need to find the percentage uncertainty in t. Because you're multiplying t by t, you must add the percentage uncertainties. Okay? And once you found that, when you found the percentage uncertainty of t squared, here, percentage uncertainty, you need to work out the absolute uncertainty. So we'll do that step by step. First, find the percentage uncertainty in t, which is 0.1 over 0.8. Okay, so 0.1 over 0.8 times 100 would give us 12.5. So 12.5% is the percentage uncertainty of t. We multiply it by 2 to find the percentage uncertainty of both together. And that gives us 25%. Now we kind of have to backtrack a little bit. If t equals 0.8, then t squared equals 0.64. So now we have that, we need to work out what is 25% of 0.64. If you plug that into your calculator, you will get plus or minus 0.16. Now, remember, significant figures are super important, and in fact it says the appropriate number of significant digits in the question. That means there's something tricky going on. Well, let's have a look at the data. 0.8 is one significant figure. So we need to make sure that 0.16 is in one significant figure. So we must bring it back to 0.2. It rounds up. And once again, don't forget the units. 0.2, I'm going to write it here. 0.2 is the final answer, plus or minus 0.2 seconds squared. Okay, the next question, use the graph to determine the value of k without the uncertainty. So I can't flick back to the graph to just give you some guidance. Make sure your read-offs are clear so that it can be looked at by the examiner, and make sure they take up more than half the line. Okay, if you're not sure what that means, if I sketch it out here, here's the line. Okay, so choose two large read-offs so that this is more than half the line and this is more than half the line. Now your gradient value should be equal to 0.30, but a range of 0.28 to 0.32 are accepted as okay. Now if we go back to the original equation, it was t equals k 1 over a half to the half, and in order to make that linear, we make t squared equals k squared. Might not have said that, but I think I wrote it correctly. K squared 1 over L. So on the line that you've worked out the gradient. Your gradient is actually equal to k squared. Okay, so this value here is equal to k squared. So now you must square root it in order to give you the actual value of k. Okay, which will give us a value of k equals 0.55. Okay, so it's also accepted the full range of 0.53 to 0.57. Now, lastly, state the units of k. On the y-axis, we have seconds squared, and on the x-axis, we have meters to the minus 1. But we need to square root that because these, or seconds squared over m to the minus 1 will give us the value of k squared. So if we square root both of those, we're left with seconds divided by meters to the minus a half. Oops. And because we're dividing a minus a half, then this actually becomes linear. So you end up with seconds times m to the plus half. Okay, so seconds, meters to the power of a half. Strange units indeed. But again, this emphasizes, I think, the lesson for this particular question, which is be careful with the units of your uncertainties and the units of your gradient. Always remember to include them.